small startup, essentially,
Yeah.
in Pleasanton, right?
Yeah, we have
Yep.
offices in Pleasanton, Denver, and Houston.
All right. So without further ado, David.
Okay, so glad to be here. What we're going to do is over the next couple days, this part of the lecture series was labeled as EM methods, but we're going to kind of break it into two different classes. We're going to spend 2 to 3 lectures on what are known as resistivity methods, which is basically a zero frequency form of electrical prospecting. And then we'll have 1 or 2 lectures of electromagnetic methods, which will mostly focus on ground penetrating radar, given the fact that a lot of students in here are civil engineering students, and ground penetrating radar is quite often used in civil engineering applications. So with that, I just want to say there's a nice online reference here that's out of the University of British Columbia, and the PDF of the presentation I'll be going through over the next few days has been posted on the website, so you can download it and have the notes with you for reference. I'm not following any certain book here or anything. I'm just trying to put this together given the amount of time that I have, plus what I think really kind of illustrates the concepts of these various methods. So, DC resistivity. You all remember your basic undergraduate physics courses, right? Where you did experiments with resistors and conductors, and there was basically you would put a current through a resistor and you measure a voltage across the resistor. Well, with DC methods, basically what we're doing is we're measuring or imaging or detecting the resistive or resistor structure in the earth. And you could think of it, there's a little figure up there. We're putting a current into the earth, and you could think of the earth as a series of resistors all connected end to end in series and in parallel, so you get a resistor network. And then we're going to go to some other part of the earth and measure the voltage. And by doing this at multiple places, injecting a current at multiple places, measuring the voltage at electrical place at many places, what we're going to do is we're going to try to deduce what the basically resistance of all those little resistors are in the earth, and then from that we can deduce things like structural properties, porosity, and fluid content. Okay, so that's kind of the generalized simplification. So let's just start at that place and talk about Ohm's law. So when we did these experiments in class, in our physics class, if you remember, what Ohm's law relates is the voltage that you apply across a resistor of known resistance to the current. So you inject a current into this resistor. That is, you put do we have a stick here? So you've got some sort of current injection that's causing a current to flow in this wire right here. And then you've got this resistor. If you remember, a resistor looks like this little kind of cylinder thing that you put in the network. And you measure a voltage across that. And it turns out that that voltage is basically, well, the resistance of that resistor is basically the voltage that you measure divided by the current, okay? So it's a linear scaling type thing. Now, the Earth isn't this nice little cylindrical electrical unit, but rather it's basically rock. So if you take the case of water and sand, and you have a cube, say, of rock or a cube of water and sand, you can break that down into 2 geometrical elements. That is the length of this block, and then the area of the face through which the current is passing. And you could think of this block of rock or sand then as that resistor unit, okay? And so then we inject a current, just like we did before, so the current's flowing here. It flows through this side of the block with this area A, or it flows in this direction, I guess. And then that block has a length L in the direction that the current's flowing. And it turns out then that you can calculate what's called a volumetric form of Ohm's law, which is given by this expression right here, where rho is what's known as resistivity, okay? Now the resistor up here had units ohms. Rho, the resistivity, has units of ohm meters, which comes from take the resistance of this block, multiply it by the area, and divide it by the length, then you come up with the units ohm meters. Okay? Now we also are representing the field rather than just I and V, we're representing the field in terms of the electromagnetic field components here. E is the electric field, which has units of volts per meter, so that would be the same thing as this voltage, except it's divided by the length between the two electrodes over which you're making the measurement, or the distance between the two electrodes that you're making the measurement. And I is what's known as the current density, which is basically the same thing as this current that you're using right here, divided by the area of the face through which the current is passing. And then, once again, rho is the electrical resistivity. Now, there is something called the electrical conductivity, which is simply the inverse of the resistivity, or 1 over rho. And it has units. Sometimes in some of the older literature, you'll see it have the units of mhos per meter. That is, they just reverse ohms and call it mhos. But more recently, in the more recent literature, you'll see it in terms of Siemens per meter, or millisiemens per meter, where this name right here, has everybody heard of the company? It's a German company, Siemens, the big electrical company. That's named after the founder of that company. Okay, any questions at this point about Ohm's law and the relation to electrical resistivity? Okay, so what range of resistivities do we have in rocks? And what are the different conduction mechanisms that we have? Well, there's several different conduction mechanisms. The one that's going to be probably of most use to all of you is what's known as ionic conduction, and this is basically you have a fluid saturated rock, or maybe it's not saturated, but you have fluid in a rock filling the pore space. And in most cases, that water, that fluid, will have dissolved ionic species, whether it's normal sodium chloride or potassium chloride. But basically, water is a very good leaching agent, and it leaches out ions into solution. And it turns out those ions carry a charge, and therefore can conduct a current. So the most dominant electrical conduction mechanism you will see is what's known as ionic. However, there are some cases where we will see electronic conduction. That's what occurs in a wire when you hook up a current to a wire or to metal. That's a form of electronic conduction where the electrons in the outer shell transfer from atom to atom, therefore allowing for an electronic current to be conducted. And you see this in graphite and in metals. Now, as I mentioned, this isn't usually the case that we see, but there are, in the mining industry, in the search for precious metals, these mechanisms do form, there are actual graphite in the rock, or certain types of iron ores that will have an electronic conduction that's very, very strong. And then there's another type of conduction known as surface conduction, and this occurs when there's clay present. I'll talk about that a little bit more. The last type of current conduction is what's known as dielectric current conduction, and this is a high frequency that occurs due to dielectric properties of rock, which is a very high frequency type of phenomena. And so we'll talk about that when we get into the EM methods towards the end of these series of lectures. So what this graph right here then shows, you've got resistivity on this axis, or on the lower axis, the inverse of resistivity, conductivity in millisiemens per meter. And this is just giving you a range of the different resistivities or conductivities of different types of rocks. Now I want you to note the scale here. We're going from 0.01 ohm meters for very, very conductive things up to 100,000, okay? Notice that this is in a logarithmic scale. There's a wide range of electrical property values that exist naturally that exist naturally. And you compare that, say, to density, which you've already studied, which has ranges, maybe 1.5 up to 3, maybe a little bit higher than that. So very small range of densities, or seismic velocities, Once again, you're going from something, you're not having logarithmic changes in seismic velocity. So one very interesting thing about the electrical methods is the wide range of values, which means you have different, in some cases, even though you might not have much of a change in a property that's yielding the resistivity change, if you, for instance, are looking for salt water versus fresh water, there's a huge change in resistivity that will yield a very measurable signal. So just to go through these real quick, down here on the very conductive side, you've got massive sulfides and graphite. Those are basically things that are formed from metamorphic or igneous activity. The massive sulfides are often mining targets that yield valuable iron ores, nickels, gold, other types of minerals, valuable precious metals might be associated with these massive sulfides. Salt water. Notice that salt water has a very low resistivity. So when you get near the ocean, for instance, there might be things that happen called saltwater intrusion, where aquifers are being pumped for fresh water, and that brings in salt water from the ocean. You can often track the saltwater front using these types of methods by measuring the electrical properties of the subsurface. Notice as we go to fresh water, the resistivity increases because we're reducing the amount of ions in solution as we go to fresh water. And then you've got ice, which tends to either sea ice or permafrost, which tends to be much more resistive.